In this video tutorial number 18, I will be using the motion design application within 3D Experience in order to solve a problem that is done in Merriam and Craig's book on dynamics. Basically, we have a setup like this. So the shaft turns at some given angular velocity. And what we want to do is to find the static, essentially static moment, reaction moment at the point O using the software. Now, the problem is stated like this in Merriam, I believe 7th edition of Merriam. The only thing is that it gives you the mass of these two plates. It doesn't give you the height of it. So what I have done is, because the mass is given to be 2 kilogram, based on a height of 5, I made the assumption that the height of this is 5 millimeter, and I have the mass, and based on that, you can get the density that the material is made of. Notice that here I had the mass of the plate. I made an assumption on the height of the plate or the thickness of the plate. That gave me the density. So this is the information, this density is the information that I'm going to put in the 3D experience later on. The problem is solved analytically in Merriam and Craig, and here is actually coming from their hand calculation. And what happens is that the bending moment about x and y, these bending moment about x and y, at all times is 9.42 for each one of them because of symmetry, and therefore the total moment is the square root of the first one plus second one squared, 13.33. So we're going to be comparing our results with this. The other thing is that, uh, as you'll see in a minute, this density and that geometry that I'm going to make is going to give you a mass of 2.003 kilograms. So about 3 grams difference between the two, but that's fine. So I'm going to call this thing the lower plate, top plate, shaft, and the bearing. And I create a rigid joint between the plate, top plate, and the shaft, between the bottom plate and the shaft, and there's going to be a revolute between the shaft and the bearing, which you have uh, you have to specify the speed on it. Now, uh, these are the dimensions that I'm going to be using, and these are the height dimensions, and we're going to be comparing our results, as I said, with that uh, hand calculation here. Okay, let's get it. Okay, this is not the best way of making the model. However, I do it in a way that is a little bit longer, but it avoids some of the complication that may run into if you do it a different way. So my strategy is to make the bearing first, and then the shaft, and then two plates, lower plate and upper plate, although they are the same, and in fact one you can make a copy of one and use it, but I'm not doing that. Okay, uh, so let's go ahead and start with the bearing. uh, Insert 3D part. I'm going to call this thing the bearing. Let's maybe let me make it reddish. The bearing is fixed, so it's not going to participate in the calculation, but you need to do that. So let me go to part design. On that horizontal plane, I will sketch a circle. Dimension this thing. The inner radius, I'm going to make it 5. And another circle. Oh, this is completely arbitrary. I'm going to make it 10. All right, exit, and I'm going to pad it. And notice that on purpose, I'm going to make it in the other direction. Right. And just for my reference, I'm going to make a coordinate system right here. This is not needed, but it helps me a great deal to orient myself. So let me go to Essential. Here's a coordinate system right there, and say, OK, good. So the bearing is made. Once again, I want to remind you that because the bearing is stationary, the mass of it doesn't matter. I'm not going to worry about that thing right now. Let's go and do the shaft. Double click. So let's insert another 3D part, call it the shaft. The shaft is also will be also massless because its mass is not taken into account when I did the hand calculation or when Miriam did the hand calculation actually. So call it shaft. Let's make the color of it orange. Let's go make it. Double click on that same horizontal plane. I will sketch. All right, well, I can draw a circle of the exactly same size, or I can project that circle. I'll make it again. So here it is. That is radius 3 millimeters. Good. Sorry, hang in there. Uh, yeah, 3 millimeters. Okay, that's good. 3. And then exit. And then pad it up. Why don't I make it 180? There we are. Now, it may bother you that these are not the same size. It really doesn't matter. It's a revolution. But if it's concerning you, then what I can do is I can go to that first part. And that radius should not have been 10. It should have been 5. This is really totally irrelevant, but oops. Yeah, make it 3. Exit. There we are. Now they're the same size. Okay, good. Okay, so now let's go ahead and make the what is that? The lower plate. Okay. So what I'm going to do is I'm going to insert 3D part. I'm going to call it lower plate. I'll make the color of it yellow. Say OK. Now we go to part design, to this part. Why don't I create a plane which is 75 millimeter above the XY plane? So let me do that. Plane offset from this by 75 millimeter. Good. Now in this, I will actually make that shape. Okay, so let's go ahead and do that. On that plane, I will sketch. Okay, so let me go ahead and make a an arc centered here. Go like that. Go like this. Let me dimension this thing to be 150 millimeters. Good. I clean this up. So what do I mean by cleaning it up? So perhaps close it with a line and another line. Okay. Now why don't I make a two concentric circles here? Please note that this is not the best way of doing this thing. There are easier ways of doing it. There are faster ways of doing it, but this is the route that I'm taking. And another one, oh, let me dimension this thing by the way, so that it is actually 3. The inside radius of this thing is 3. Good. And then I'm going to make another circle. Make the radius of it 5. And we go use the quick trim to be able to create the hole and things like that. So let me see now, where's the quick trim? Right here. So for example, a bunch of things I want to delete. I want to get rid of this. I want to get rid of that and this. And let me see. So we want to get rid of this thing. I think we can actually go ahead and pad this thing. If not, we go clean it up. Okay, yeah. Oh, this one has to go too. Let me double click on it again. So let's do another quick trim. Let's do this. Okay, now exit. There we are. We're ready to pad. So let's go ahead and pad it by symmetrically 2.5 millimeter in each direction, which gives you a plate thickness of 5 millimeter. Okay, good. So we go all the way to the top once again. Once again, we go to the top and then we make another plane. Oh, insert top plate, insert 3D part, call it top plate. And once again, the color of it, I'll make yellow. Say okay. Let's go ahead and make it. Double click on it. Notice that the plane, the part has been created. Now I want to create a plane offset from the XY plane by a height of 150 millimeters. There, this is the other plane. On that plane, I will sketch. Okay, so exactly the same routine. So it's okay. I'll do it again. Okay, let's dimension this thing to be 150. Good. Now close it. Let's drawing those two circles. Normal view. Okay, the two circles just like that. I can project it if I wanted to, but it's just as easy. Let me hide this thing actually, and hide the shaft, and hide the bearing. Yeah. Okay, so let me go ahead. These things I'm going to hide. I don't want to see them. Okay, so let me make two circles here. One of them radius 3 millimeters, and the outer one 5 millimeters. Use quick trim to clean it up so that we can actually pad stuff. So let's see, what do we don't want? We don't want want some of this stuff. We don't want this. We don't want that. We don't want uh, this. And I think I'm missing something. Yeah, these two should go too. I think now it's pattable. Let's see. Yeah, that's pattable. Excellent. So we're going to go to pad in both direction, 2.5 millimeter in each direction. So that gives you a thickness of 5. So some stuff are hiding. Let me bring them in the front. So this was hiding. This is hiding. What else is? The bearing is hiding. Oops. Bearing. This is the bearing. Yeah. Okay, so let's go ahead. So this is it. There are no constraints here. I made them so that they are in position, the right position. Okay, so let's do a quick save here. Now we're going to apply materials. So what we do is all I do is to apply material to this top plate and the bottom plate. They're identical. I don't have to worry about the bearing and the shaft because later on they're going to be declared as massless anyway. So let's go ahead and to tools, create a material. I'm going to call it video 18, and say OK. Notice that it's going to be created here, but I have not put in any numbers yet. So basically, it's a template right here, video 18. So I'm going to say apply. Let me close this. So I'm going to apply it to the lower plate, and we're going to apply it to the top plate. Both of them right there. Say OK. Now, if we go to one of them and we can input the value, so we go here. For example, this is a lower plate. Doesn't matter. Double click on the video 18 material. One more time. Here's the core material, and I'm going to put 22. What was the number? 22,635 kilogram per meter cube. 635. Oops. 635. Okay. And then say apply, and then close it. Now notice that here, even if you go to the other fellow, the one with the top plate, you double click on that, that number should appear there, although I didn't input it there, it appears there. Now, notice that I don't need to go to material simulation and then, put the number in there. The core material is going to be used. Okay, very good. That's pretty much it. Okay, so we're good. Now we're going to go to motion design. Oh, I forgot to do the cancel that. Actually, let me kill that. I forgot to create the constraints, assembly constraints. So let me go ahead and do it now. I forgot to do that. So we go to assembly. So now we're going to apply assembly constraints. So let's go ahead and apply, first of all, fix the bearing. So assembly constraints. Oh, go all the way to the top. Okay, assembly constraints. Fix the bearing. There's the bearing. Fix it. There we are. And then create a rigid joint between the shaft on the top plate and shaft on the lower plate. So rigid. Where's the rigid? Rigid. We use this template. Makes no difference between this guy and the shaft. And close it. Oh, and do another one. Same template between this fellow and the shaft. Close it. And then we want to revolute between the shaft and the bearing. So let's go to the revolute. Where's the revolute? I'll use this template. It really doesn't matter. Axis and axis, plane, plane. So let's do that. This axis and the axis of the bearing. And for example, the plane of the bearing over there. And there are easier ways of doing this thing, but I want to zoom in here, right here, the bottom of that shaft. And then I don't need this last set of selections, so just delete it, and we can close it. So a revolute has been created here. Let me update these things. And now we're going to go to motion design. Motion design. New mechanism is going to be created. There's going to be a couple of things we're going to check. Okay, let's look at the joints here. See the joints? These are the joints. Rigid, rigid, revolute, fix. Okay, very good. And see the bodies. Bodies. Let's look at, for example, the lower plate right there. If I double click on this thing, what I'm going to get is the information about the mass of the lower plate, which is 2.003 kilograms. It's a little bit different from the value that's specified here because I'm not, there's a little bit of extra area or volume or mass because of that thingy, that hole. Okay, good. It's okay. It's 2.003 kilogram versus 2.2 kilogram. Okay. The other thing is, let me also check some of the stuff here. Look at this number, 9.291 to the 10 to the minus 4, and that matches, uh, where is this thing? Right here, half of that. Okay, half of that, right there, half of this. Okay, which is essentially that kind of a thing. Let's check the other guy. Those are. Let's check the top plate. Mass is the same, and you see this number. It's it is not quite what I expect to get in here, but we'll see. It's going to work. Okay. Now, as far as the bearing is concerned, double click on it. Because I did not put any material on it, it uses default properties of steel, but I don't want it. I'll make it rigid massless. Okay, say okay. And the same thing with the shaft, double click on it. It uses the properties of steel. I don't want it, rigid massless. We say okay. Good. So what do we need? Okay. So we want this thing, this revolute to turn, this shaft to turn at 300 turn per minute RPM. So let's go ahead and create a driver right there. And to join, which joint? Is that the revolute joint? Click on this box to specify the speed. You go click on it. Wait. Okay, right there. So we want to specify the angular velocity, and we want 300 turn per minute or RPM. Turn, this is the unit, turn underscore MIN. It's going to convert it to rad per second right there because that's what the unit default unit is right now. I didn't change that. So we say okay. And then we say okay. Now let's simulate this thing. Oh, gravity is automatically applied, but it's not going to come into the picture because this is a revolute joint. Because this is a revolute joint, gravity is not going to be accounted for. And in fact, what I'm going to do is, if I wanted to, I can go global and deactivate this. Okay, it really doesn't matter. Now, let's go ahead to duration of the simulation. So if you double click on this, it's going to do it over 3 seconds. Why don't I do it over, I don't know, 1 second, 2 seconds? I'll make it, yeah, 2. Makes no difference. And then we can actually preview it right here. This thing should turn. If it doesn't turn, we've got to go fix something. This is a preview. This is not running yet. Just give it a minute. If it doesn't turn the way we want it, then obviously we have to go fix stuff. But it did. So exit that. Now we're going to run it. So we go to simulation, run it. And it says succeeded. Say OK. If you go to results, you click on the 2D plot. Notice that we're gonna select the joint here. Where's the joint? The revolute joint. Where is the joint? Revolute joint. And notice that we can plot the torque and the force with respect to x, y, and z. So let's look at x. What is that? Right there, 9.42. 9.42. This is x. If you select the y, it's going to be the same value. Oops, what did I do here? Not force, I'm on the torque. Yep. Again, they're sitting on top of each other, 9.4. So the magnitude of the moment, static moment down there is square root of 9.42 squared plus 942 squared, which is 13.3. And we're getting exactly the same answer that hand calculation in Merriam and Craig gives you. Okay. The only thing that I don't like is this. For one of them, it gives you the same number that is in the hand calculation. The other one, uh, my guess is that it's calculating these things with respect to mass center, which is not wrong. It's just that when it comes to hand calc, when it comes to simulation, it has to be adjusted so that we get the correct value. Okay. So because if you look at it here, you go back here, let me say okay. If you double click on this, what is that? Bodies, right there for not the shaft, but the lower plate or the upper plate, it really doesn't matter. So for example, look at the top plate. Uh, this information is with respect to the mass center reference frame, okay? That's why the numbers are the same. If you use that lower coordinate system down here, then it will give you the same value that Merriam and Craig gives you. Now, something that is really weird, let me, uh, I'll do that in the next video, something that you've got to be very careful. And it doesn't pertain to this particular problem, but uh, some stuff are not updated. If you go and change the density, unfortunately, it doesn't show up in this run. For example, let me show you. Go here, go to the part design. Let's go to the here. Let's go to this material. Double click. Let me change this thing to, how about, I don't know, 2 kilogram per meter cube. Apply, close. Now, first of all, it is reflected in the other part. You can see that if you double click on it, no problem. Right there, good. Now, If you go back to this physics simulation, even if you update it, even if you update it right there, and even if you say update body weight, and now you go and double click, for example, on the top plate or lower plate, makes no difference. That number did not change. That's really bothering me. Be careful. Didn't expect this thing to happen. Anyway, we solved that problem. Good luck.